Hello everyone, welcome to this lecture. So, in this lecture we will continue our discussion on groups and we will introduce a very special class of groups called as cyclic groups. Let us first prove that the identity element and the inverse element, they are unique in any group. So, let us first prove for the identity element. So, imagine you are given an abstract group G, then my claim. So, of course, G has to have an identity element because that is one of the group axioms, but we want to prove that it has a unique identity element E. That means, you can't have multiple identity elements and the proof will be by contradiction. Okay. So, on contrary, imagine that you have two distinct group elements E1 and E2 and both of them are identity elements. So, the proof by contradiction paradigm tries to arrive at a contradiction. So, let us see what contradiction we can arrive at. So, since both E1 and E2 are identity element, as per the requirement of the identity element, the following holds. You take any element A from the group, the result of E1 operation A will be the same as the result of E2 operation A, and both these answers will be same as A. Okay. That is what is the property of an identity element. Okay. So, the E1 operation A should give you A and E2 operation A also should give you A. So, that is why I can say that E1 operation A is same as E2 operation A, but if that is the case, then I can apply the right cancellation rule and come to the conclusion that E1 is same as E2, which is a contradiction because I assume that E1 and E2 are distinct elements. So, that shows that you have a unique identity element in the group. Now, next I want to prove that in any abstract group, if you take an element A in the group, then corresponding to A you have a unique inverse element in the group. You can't have multiple inverse elements in the group. Okay. So, again the proof will be by contradiction. So, on contrary, assume that you have multiple inverse elements for this A. So, imagine that you have two distinct inverse elements. So, the first inverse element is this A1 inverse and the second inverse element is A2 inverse, and since I am assuming they are distinct, that means they are different. Now, the property of the inverse element is that if I perform the group operation on the inverse and the element, I should get the identity element. So, the result of A1 inverse operation A will be the identity element and the result of A2 inverse operation A will also be the identity element. So, if both of them gives the identity element, then I get the conclusion that the result of A1 inverse operation A is same as A2 inverse operation A. But then if this is the case, then I can apply the right cancellation rule and come to the conclusion that A1 inverse is same as A2 inverse, which goes against the assumption that A1 inverse and A2 inverse are distinct. So, that shows that every element in the group has a unique inverse. Okay. Now, we want to introduce a new operation in the group which we call as group exponentiation. By new operation, I mean to say my operation is still O, but I will be using that operation O multiple times on an element of the group, which I can view as some kind of group exponentiation. So, then in the regular arithmetic, when I say A to the power x, it is interpreted as if I want to multiply A with itself x minus 1 times. Okay. So, I want to abstract out that operation in the context of a group itself. So, imagine you are given an abstract group and without loss of generality, I will now follow the multiplicative notation. This is just for our convenience because we are accustomed to multiplicative notation while discussing exponentiation in the regular arithmetic, right. So, that is why I am using the multiplicative notation, but whatever I am discussing, that is true even if my group operation is additive or it is treated as an abstract operation O. So, since I am following the multiplicative notation, I will be using 1 for denoting the identity element E. 1 does not mean the numerical 1, remember. Okay. And I will use a power minus 1 for denoting the inverse of the element A. Again, a power minus 1 need not stand for 1 over A. It depends upon my exact group. Now, the group exponentiation for any group element is defined recursively as follows. Okay. Because in the regular world also a power x can be defined recursively. So, I define a power 0 as 1 in the regular world, and then I defined a power 1 as 1 a, and then I can recursively define a power x as the result of a power x minus 1 with a. Similar definition I will now use in the context of an abstract group. Okay. So, I will define g power 0 to be the identity element. This is a definition, okay. And I will define g power 1 to be the element g itself. Now, I will define g power m to be the group operation performed on the element g and the element g power m minus 1. So, remember g power m minus 1 is also a group element, because g power m minus 1 is further recursively be defined as g power m minus 2 into g, which will be again recursively defined as g power m minus 3 into g square and so on. So, this will be a group element and g is a group element, and I am following a multiplicative notation. So, this multiplication actually stands for the abstract group operation O. So, whatever result I will obtain by performing the group operation on the element g and the element g power m minus 1, that will be defined as g power m for every m greater than equal to 2. I can define even the negative powers of my group element. So, g power minus 1 will actually stand for the multiplicative inverse of my element g, and g power minus m will be recursively defined as follows. I will take the multiplicative inverse of g, and I will take this group element, namely the group element g power minus of m minus 1, and I will apply the group operation, and whatever is the resultant value, that will be called as g power minus m. So, this is the way I define the group exponentiation, assuming that I am following a multiplicative notation. Corresponding definition will be there if I am following an additive notation. Now, it turns out that the rules of integer exponentiations that we are aware of are applicable even for group exponentiations. So, let us see. So, imagine I am given a group element small g, and I take exponents m and n. They could be positive, they could be negative, they are some arbitrary exponents. Now, it turns out that if I take the group element g power m, and if I take the group element g power n and perform the group operation, then that will give me the same group element g power m plus n. Okay. And this g power m plus n can be obtained by recursively following this definition. Okay. So, what I am saying is, on your left hand side you have two group elements and we are performing the group operation on them. So, we will get one group element, call it A, and you have g power m plus n, which is another group element whose value I can obtain by following this recursive definition, call it B. My claim is A is equal to B. The group elements A and the group elements B are same. So, you can easily follow that. In the same way, if I take the group element g power m, so say g power m is A, and then if I compute A power n, then that will be the same as the element g power m n. So, g power m n also will be some element, call it B. So, A equal to B, and g power m n will be the same as the element g power n, call it C, and C power m. So, all of them will be same. Okay. It is easy to verify this rules are applicable even in the context of group exponentiations. Okay. So, now let us define order of a group element. So, imagine you are given a finite group, and for convenience I will be using a multiplicative notation, but again whatever we are defining here holds with respect to a group where my notation is additive. Okay. And now consider an arbitrary group element small g. Okay. Now, let me define a function here. I am defining a function from the set of natural numbers to the group, and my function is the following. So, the domain will be 0, 1, 2 up to infinity, and the codomain is the group. And the way I go from the domain to codomain is if I want to map the element I go to g power I. Now, it is easy to see that since my group G is a finite group, it will have finite number of elements, whereas my domain is infinitely large. Then by pigeonhole principle, I know that there exist two values, at least two values A and B, where A and B are both non-zero and A is greater than B, such that both A as well as B get mapped to the same group element, namely g to the power A and g to the power B are same, right. That comes from pigeonhole principle. Now, if g to the power A and g to the power B are same, then if I multiply with the element g power minus B on both the sides, multiply in the sense I perform the group operation on g power A and g power minus B, the result will be the same that I will obtain by performing the group operation on g power B and g power minus B. And g power minus B is indeed a group element, because g was an element of small g was an element of the group, and g power minus B is well defined as per my definition of group exponentiations. But now, what can I say about the right hand side? Since I am following the multiplicative notation, I can say that the result of g power B group operation g power minus B will be the identity element, and the identity element in the multiplicative notation is 1. And what will be my left hand side? As per the rules of exponentiation, it will be g power A minus B. Now, I know that since A is greater than B, A minus B is non-zero and it is positive, A minus B is positive, okay, because A is greater than B. Now, I know that since A minus B is positive, that means there is at least one positive integer n such that for the element g which I have arbitrarily chosen here, g power n is 1. Of course, there might be multiple values of n for which g power n will be 1. It depends upon how many A B pairs are there. Okay. But at least one positive integer n is definitely there such that g to the power n is the identity element. Now, among all those positive integers n such that g to the power n is equal to the identity element, the smallest positive integer is called as the order of the element g. Okay. So, that is the definition of the order. So, let me write it out here. So, let G be a finite group, and for convenience assume we are following the multiplicative notation and small g is a group element. Then the order of the group element G is the smallest positive integer n such that g to the power n is 1. So, the above definition for the order of a group is with respect to a finite group, because if the group is infinite and if you are now taking an arbitrary group element, then it may not be the case that you can easily find out the n, or whether at the first place we do not know whether such an n exists or not if my group is infinite. So, in that case I will say that the element G will have an infinite order, but for the finite groups the smallest positive integer such that g to the power n is the identity element will be treated as the order of the group element G. So, now let us discuss some interesting properties of the order of a group element. So, again I will stick to the multiplicative notation. So, imagine you are given an element G and it is given to you that its order is n. That means I know that g to the power n is 1. Then my claim is the following: if you have g to the power s also giving you the identity element, then that is possible if and only if s is a multiple of n, that means s is completely divisible by n. Okay. Of course, for s equal to n this claim is true, but my claim is that if at all there is any other s such that g to the power s gives you the identity element, then s has to be a multiple of n. So, we want to prove this, and this is an if and only if statement. So, I have to prove two implications here. So, let us first prove the implication in one direction. So, assume s is a multiple of n. Okay. So, I want to prove that if s is a multiple of n, then this direction implication is true. I want to prove that g to the power s will give me the identity element, given that g to the power n is identity element, because it is given that the order of g is n. So, since s is a multiple of n, by the way I am giving a direct proof here. So, assuming my premise is true, since s is a multiple of n, I can write down that s is some m times n, where m is some integer. Then what can I say about g power s? As per my group exponentiation rules, it is same as g power m n, and g power m n I can break down as the group element g power n being raised to the power m. But since g power n is the identity element, this is same as the identity element raised to the power m, and identity element raised to power m means I am operating the identity element with itself several times, namely m times, which will give me again the identity element, namely 1. So, that proves the implication in one direction. Now, let us prove the implication in the other direction. I want to prove that if there is some exponent s such that g power s is 1, then definitely s has to be a multiple of n. So, again I will give a direct proof here. So, I can always write down my exponent s as some quotient time n plus a remainder, where the remainder will be in the range 0 to n minus 1. And my goal is to show that s is completely divisible by n, namely I want to show that my remainder r is 0. Now, again I am giving a direct proof. So, I am assuming my premise to be true. Since my premise is true, that means g power s is 1. And now, I am writing down the value of s in terms of the quotient and the remainder. So, I get this equation. Now, I can rewrite g power m n plus r and break it as per the rules of group exponentiations like this. I can write it out as the result of group operation being performed on g power m n and the element g power r, and my right hand side is the identity element. Now, I can further apply the rules of the group exponentiation and say that g power m n is same as the element g power n being raised to power m, and g power n is the identity element. So, this gives me 1 power m, which is 1. That means, this is identity element or 1, and 1 multiplied with g power r will be giving me the element g power r itself. So, I get g power r is equal to identity element. So, remember that my range of r is 0 to n minus 1. So, my conclusion now is the following: since g power r is equal to identity element, r has to be 0, because if r is not 0 and if it is strictly less than n, then I get a contradiction to the fact that n is the smallest positive integer for which g power n was identity element. Okay. So, that shows the implication in the other direction as well. Okay. Right. So, now let us define what we call as cyclic group. So, it is a special type of group. The speciality is the following. So, you are given a group with some abstract operation O. Okay. It may or may not be a finite group. The speciality of the group is the following: it should have an element small g, which we call as a generator, and it is called a generator because you take different powers of this generator. Again, by power I mean group exponentiation. That means, you perform group exponentiation on this generator multiple times, 0th time, 1 times and different times, right. You will get all the elements of your group. That means, this element small g has the capacity to generate all the elements of your group by performing the group operation group exponentiation on this generator. So, if we have this special element, namely generator there available in the group, I will call my group as a cyclic group and I use this notation. This notation basically says that this is small g can act as a seed, it has the capacity to act as a seed and reproduce the entire set big G by performing or by raising or by computing different powers of this generator. Of course, there can be multiple generators possible in a group, in a cyclic group. What cyclic group says is that if you can show me the existence of one generator, at least one generator, I will call the group as a cyclic group. You might be wondering why it is called cyclic, what exactly the term cycle here mean, it will be clear very soon, right. So, as I said, a cyclic group could have multiple generators. So, before proceeding further, let us see some examples of a cyclic group. So, consider the infinite group, namely the group of namely the group based on the set of integers with respect to the plus operation. My claim is that the integer 1 constitutes your generator. This is because if you take different powers of this element 1, it will give you all the elements of your integer set of integers, right. So, let us see whether we can generate any arbitrary integer x by computing some power of this element x. And indeed, it is easy to verify that you take any integer x, it will be some k times 1 for some integer k. So, for instance, if you want to generate say the element 0 from this element 1, then I know that 0 times 1 is equal to 0. That is the definition of my group exponentiation. That means, remember I defined g power 0 to be the identity element when I followed the multiplicative notation. The additive notation will mean that if I add g 0 number of times, that will give me the identity element for any g. So, I am now treating g as 1. So, that means 0 times 1 will generate the element 1, whereas if you want to generate the integer 1, then it is same as you perform 1 to the power 1. 1 to the power 1 in the additive notation will be treated as 1 times 1 and that will give you 1. If you want to generate the element 2 through the element 1, then that is same as performing the operation plus on the element 1, that will give you 2. So, this can be treated as 2 times 1 and so on. So, that means all the values now in the positive side can be generated by the element 1, and in the same way you can generate the negative elements as 1. So, for instance, if you want to generate minus 1, then minus 1 can be interpreted as if you want to perform minus 1 times 1. Okay. Minus 2 can be interpreted as minus 2 times 1. Okay. So, minus 2 times 1 is nothing but the additive inverse, namely additive inverse of 1, namely minus 1 being added to itself 2 times. In the same way, you want to generate minus 3, that is same as minus 3 times 1, and minus 3 times 1 is nothing but minus 1 being added to itself 3 times. Okay. That is a definition of group exponentiation for the additive notation. So, that shows that even though this group is infinite, it is having a generator, namely the element 1. Whereas, if I take, so this is an example of an infinite cyclic group. Now, let us take an example of a finite cyclic group. So, let P be a prime And now if I consider the set of all integers modulo p, namely the set 0 to p minus 1, and if my operation is plus modulo p, then my claim is that this group is a cyclic group, and in fact it has multiple generators. In fact, all the elements except the identity element 0 will be a generator for this group. So, if you want to verify that, so let us see, let us take p equal to 5, then my set here is 0, 1, 2, 3, 4, and my operation is plus modulo 5. Now, you can check here that I can generate all the elements through 1. So, 0 can be generated through 1 because 0 times 1 is defined to be 0, namely the identity element. 1 time 1 is also defined to be the element itself, and now 2 times 1 is basically 1 plus 1 modulo 5, and 1 plus 1 modulo 5 is 2. 3 times 1 will be 1 plus 1 plus 1 modulo 5, which will be 3, and 4 times 1 will be 1 plus 1 plus 1 plus 1, which is 4 modulo 5, which is 4. In the same way, 2 is also a generator. You can generate all the elements through 2. So, 0 times 2 will be defined as 0, 1 time 2 will be defined as 2 itself, 2 times 2 will be 2 plus 2 modulo 5, which is 4, 3 times 2 will be 2 plus 2 plus 2, you get 6, but you have to do operations modulo 5. So, you will get 1, and then 4 times 2 will be 2 plus 2 plus 2 plus 2, which is 8 modulo 5, which is 3. So, you have generated 1, you have 0, you have generated 0, you have generated 1, you have generated 2, you have generated 3, you have generated 4. So, 2 is also a generator. In fact, you can check that 3 is also a generator and 4 is also a generator, right. So, now let us derive some interesting properties for cyclic groups. So, imagine G is a cyclic group, and suppose the order of G is n. So, that means now I am considering a finite cyclic group, because since I can write down its order, that means it has finite number of elements. Let n be the number of elements, and say small g is one of the generators. Then my claim is that the order of the generator, so remember generator is an element. So, my claim is that the order of the generator is n. What does that mean? So, this means that n is the smallest positive integer such that g power n is equal to the identity element. So, since assume I follow the multiplicative notation. So, the order of g is equal to n means g power n is 1 and n is the smallest such positive integer. By the way, in the definition of order of an element, why I am focusing on positive integer? Because if I do not put a restriction on positive integer, then trivially g power 0 is always defined to be the identity element, right. So, that is why I am interested in the smallest positive power for which g power n will be 1. Okay. So, now let us prove this statement regarding the order of the generator. So, the proof will be by contradiction. So, on contrary, assume that the order of the g is not n, but some positive integer I, where I is strictly less than n. So, now what can I say about the elements g to the power 0, g to the power 1, g to the power I minus 1? Of course, they are group elements because we have the closure property being satisfied, but apart from being group elements, my claim is that all these I elements, why I elements? Because I have taken I different powers of G. So, my claim is that these I different elements are indeed distinct, none of them are repeated. Again, this can be proved by contradiction. So, on contrary, assume that the jth power of G or the generator and the kth power of the generator produces the same group element, where k is some power higher than j, and both jth power and the kth power are strictly less than equal to I minus 1. Now, if that is the case, then I come to the conclusion that g to the power k minus g is the identity element. How do I get this? By multiplying both the sides of this equation by g power minus j. Okay. So, if I multiply both the sides by g power minus j, I get 1 here and I get here g power k minus j. Okay. So, I come to the conclusion that g power k minus j is 1, but then that means that the order of g is k minus j. Why k minus j? Because since k is strictly greater than j, then k minus j is positive, and that means k minus j is not 0 and k minus j is strictly less than I, which is a contradiction to my assumption that the order of g is I, right. So, that shows that indeed the statement that all these I distinct powers of g are going to give me distinct group elements is true. But if these I powers of g are giving me the distinct elements, then how come at the first place g is a generator? Because if g is a generator, then it has to generate all the n elements of the group. Right now, I have generated only I elements of the group by raising g or by computing I distinct powers of g, and I is strictly less than n. How do I generate the remaining elements of the group? You might be wondering, why can't I go for the higher powers? The problem is that if you go to the higher powers, you start getting the elements which you have already generated through the first I powers of your generator. Namely, g power I will give you the same element as g power 0. G power I plus 1 will give you the same element g power 1. G power I plus 2 will give you the same element as g power 2 and so on. So, that means once you have computed the first I powers of g, the next powers of g will start giving you the elements which you had already generated. You will not be getting any extra or any new elements of the group, and that goes against the assumption that my small g was a generator for the whole group. If it was a generator for the whole group, then it should have the capability to generate all the n elements, not just I elements. Okay. So, that is why the order of my generator g has to be the same as the order of the finite group or the whole group, which is n. And that shows that why we are calling this group as a cyclic group, because if g is the generator, then by raising g to different powers from 0 to n minus 1, I will be getting the entire group. Now, once I start computing the higher powers of g, namely g power n, g power n plus 1 and so on, I will not be getting anything extra. I will start getting the same elements which I have generated by computing g power 0, g power 1 up to g power n minus 1. In that sense, it is a cyclic group. Cyclic in the sense you can arrange the elements of the group in a cycle, and that cycle can be completed by raising g or the generator to different powers in the range 0 to n minus 1. Okay. So, that brings me to the end of today's lecture. Just to summarize, today we saw some more properties of groups. We discussed about the order of the group, we discussed the properties of the order of the group, we discussed about the order of a group element, and we also discussed about cyclic groups and derived some properties regarding the order of the generator of a cyclic group. Thank you.